Good morning, ladies and gentlemen. Welcome to BYK-Gardner and welcome to our today's web seminar. The topic today is the ultimate way to measure black. So it's color measurement and what are the challenges when you try to measure the deepest blacks. So before we start, let me introduce myself. My name is Henrik Folkerts. I'm working for BYK-Gardner since 26 years now, and I'm responsible for training and also for the web seminars. Some general information about the web seminars. So you are muted by the system automatically. That's why please use the chat function to document your questions and I will try to answer them later. In addition, you get all the information you see today by email. I will convert the PowerPoint to a PDF file and send it out to you. And we will put a link of the recording on our website. Okay, the agenda for today is we will deal longer with the question how to describe black. So what is a good way to talk about? How should we look at it? And which numbers are useful to describe black? After that, the question will be what is the challenge about measuring black? Then I will present our solution. And last but not least, we also have to talk about the really important topic of sample preparation. But first, let's start with some beautiful, for me, beautiful pictures. So black has always been the color for cars. So this has begun with Henry Ford. You know, in those days, the only available color was black, and it's still true today. And black is still among the top 3 colors for cars worldwide. Or when you look around, so black can be found also maybe in your kitchen or at least in every area of our life. So, and here, this is a nice picture how far black can go. You see here, you see a 3-dimensional face. And now this object is coated with the so-called Vanta black, and that means it hardly reflects any light rays. We perceive only a 2-dimensional jet black surface here instead of a 3-dimensional object. This coating absorbs more or less any light or every light, sorry. And now let's discuss how can we describe black. What is the best way to talk about it? You see, black can be lighter or darker, from black to deep black to the deepest black, so the jet black. Means blackness itself only makes a statement about the lightness of the sample without considering a colored undertone. But black can have an undertone. Usually it is bluish or brownish. And the undertone of a black color has an impact on the visual assessment. So visual assessment is the right keyword. Black is really a challenge. For example, any specular reflection, here, a nice picture for specular reflection, can extremely influence our color impression. Due to that, defined conditions are required, and we have some recommendations. For example, in the DIN ISO 18314 Part 3. And this standard asks for daylight D65 and the instrument geometry 45.0 or the visual checking setup 45.0. That means light illuminates perpendicular to the sample, like here in a light booth. The light comes from here to the sample. And now the sample is evaluated under 45 degree here. So by the way, it also works the other way around. So 0.45 is also allowed. And in addition, a neutral surrounding is necessary. So in a light booth, we have a neutral gray surrounding. And the standard even recommends a dark room. On picture 1 here, you see that is our BYK-Spectra Pro. That is a light booth that offers a really good daylight simulation. And a good daylight simulation is ideal to assess smallest deviations in lightness and undertone. On the second picture, you can see a carbon black manufacturer also working with strong flashlight. And I can clearly identify two different undertones. So here it's more brownish, and here on the other side is it's more bluish. So that means I want to show this method works also quite well. Here we cannot use a light booth for visual checking. However, I would like to evaluate these samples with you. And to make life easier, we first have a look onto the brightness only. And this is here tricky with these samples. I hope you all agree that the reflection of the skylights clearly distract us from the brightness. So without this reflection, you see this is much better. On the left side, you see now the darkest sample in the fan deck, and on the right side, the lightest one. Means the one with the lowest absorption behavior here. More light is reflected. Here, a second sample set now with differences in the undertone. On the left, you can see a sample with a clear brown undertone. And now moving to this side with our eyes, here you see the sample with the deepest blue undertone. Sorry. Deep black with a bluish undertone is usually perceived as darker and more brilliant than a brownish undertone, like here or like here. And for this reason, black with a blue undertone is often preferred in technical applications, such as for top coats in the automotive industry, for example. In real life, the visual evaluation is followed often by the measurement of the samples. And for this measurement, we have to choose the right instrument. As before, the DIN ISO 18314 recommends an instrument with a 45.0 setup for deep blacks. So this really makes sense because we want to measure what we see, and the visual setup should be 45.0 or 0.45. And in addition, the following criteria are also mentioned. You see the instrument should be able to show 4 digits behind the decimal points for the X, Y, Z values. And the instrument should be able to show 5 digits behind the decimal point for the reflectance data. So that was trying to define a specific kind of accuracy. So during the rest of the web seminar, we will see if these criteria are enough. But first, before we have a deeper look on black, we look at color in general. So color is defined as the appearance that an object has as a result of reflecting light of a certain range. The concept is white light strikes an opaque sample, and then we have to deal with 2 types of reflectance from the surface. First, the specular reflection. So white light hits the surface, and from the top layer, white light is reflected, a small part of the total light, and this we call gloss or specular reflectance. The rest of the light goes into the coatings, and it is by pigment and dyes selectively absorbed, and some are scattered. So you see here parts are absorbed and some are scattered, and the scattering is the diffused reflection. And we see here the color green because all the other wavelengths of the white light have been absorbed. So, and this diffuse reflected light is detected by a spectrophotometer and can be shown as a spectral curve. In this case, again, the color we see is green because the maximum reflection here in this area is in the according range of the visible light. And as always, the spectral curve is a unique fingerprint of the sample, and out of it, the CDAP values, like here, are calculated. So in the table, you see the L star is a value of 51. So that means in the middle of the L axis from 0 to 100. And the A value is minus 32. So it's clearly on the greenish side of the A axis. A axis means green red. And the B value is plus 17. This means that it is on the positive, on the yellowish side of the B axis. The B axis is a blue-yellow axis. So we see here a rather yellowish green with a medium brightness, we can say. Now let's look to a reflectance curve again, now for a black. The definition for black results from the absence of or complete absorption of visible light. So as you can see, the definition is the complete opposite to that of color. And the reflected light in this example you see here is on a very low level at just 0.1%. And in addition, in the spectral curve, we see no peaks. It's flat, it's a horizontal line. Means we do not see any colored undertone. It seems to be a very neutral black. The next question is, when we look onto the measured values in the table here. So the question now is, are LAB values in general useful to describe those deep blacks because you see they are very close to zero. I have already mentioned that we want to measure what we see. In other words, we want to be able to differentiate samples by measurement, which we also perceive visually as different. In the graph and the table, you can see 6 samples which we received from the company Orion. The samples are made of black painted glass and named test 1 to test 6. We did a visual assessment, and our result was that the 6 samples can be distinguished in terms of brightness as well as undertone. Unfortunately, if you look at the measured values, you will see that there is hardly any difference between them. This is especially true for the A and for the B values. So meaningful tolerances cannot be defined. And the conclusion was that LAB is not suitable as descriptive values for deep blacks. So that's why in this area, measuring deep blacks, special indices are used. Um, Here you have an overview, and I do not want to go into detail in regard of the evolution of these indices, just this. They are far from new. So the first one, the M, for blackness measurement was introduced in 1976. At that time, there were no suitable instruments available, so the M was not widely used. 10 years later, Mrs. Lipogloma introduced MY and MC, and they are still used today. And the first international standard, the DIN 55979, for testing of pigments, determination of the black value of carbon black pigments was introduced in 1989. In the standard, we have the recommendation, the definition for 3 indices to describe black. So My describes the brightness, or better say blackness, of a sample independent of the hue or undertone. MC describes the degree of blackness independent of the colored undertone. Please remember that 2 samples with the same My number means brightness and different undertone can be perceived as different, dark or black. And DM describes the absolute contribution of hue or the undertone of black. So this is a nice picture. You see positive values for DM corresponds with a bluish shade. Uh, the higher the number, the bluer the shade. And negative values for DM describe a brownish shade. So this slide again shows the relationship between the amount of reflected light and the height of My as a graph. So the less light is reflected, the higher is the My and the deeper is the black. So My 400 means a really deep black with a minimum amount of reflected light. And this curve looks the way it does because my is based on a logarithmic function. And in a range in which almost no more light comes back, the my value changes drastically. So from here, let's say 0.1, that means my 300 to close to zero reflection, it changes to 400 for my. And this is the area where it is really difficult for spectral photometers. Before we look deeper into black, here a remission curve, a reflectance curve for a white. So a bright white reflects almost 100% of the light. Now, when you check here the scaling, we are here on top. While the amount now of reflected light becomes smaller and smaller with darker colors. So it has always been the greatest challenge for a spectrophotometer to achieve repeatable and reproducible results on a black color. But those really deep blacks takes the issue to a new level. So I can't show a deep black curve in the same resolution. So here we need a magnifier. So, and now here you see a spectral curve of a deepest black. But to show what disturbs this low signal, I need a magnifier again. So the same curve. And now the scale is not from 0 to 100. Now the scale is from minus 0.1 to 1. So 100 times magnified or shrink the other way around, sorry. And now we have to look at the noise. So what is important, let's say noise is in electronics an unwanted disturbance to the signal. And what is important is to have a good signal to noise ratio. And you see the signal to noise ratio in this relation is a problem for the signal because they are close to each other. And here you have to optimize your instruments to get a better signal. So, and one way to do that is to increase illumination, for example. So let's say we can turn the light on. So we increase the light we send, and in this way we can increase the signal, for example. So by doing that, we get a signal that is significantly greater than the noise level. So here you can see how much the signal has improved. We have 20 times more useful information with consistent noise. The noise remains here. And this leads to a significantly higher accuracy. And this is only one option we have to get a better signal. So here just as an overview, available for measure color and the deepest black are special models of our instruments. We have a handheld, portable Spectro 2 guide called Spectro 2 guide. And from the Spectro 2 guide, there is a Spectro 2 Guide Pro model available. And also from our benchtop instruments, the Color 2 View, there is a Color 2 View Pro model available. And they have an optimized setup. So to increase the signal to noise ratio, to reduce the noise, you need an adapted production process, and you need other electronic components. You need high power LED, and you need an extended illumination time. And during the production process, you need a different calibration setup, and different calibration tiles are needed to check these instruments. And with all these modifications, you get instruments with improved performance on the deep blacks. So now, again, let's take another look to our sample set test 1 to test 6. Now we have bar charts here instead of the spectral curves. And the blue columns corresponds to the average MY number after 50 measurements. And the according y-axis is here on the left side. These orange dots here show the average DM, so the undertone, after 50 measurements, and the related y-axis is here on the right side. And in the table, you see instead of the LAB values, now the indices, MY, MC, and DM. And MY is now between 230 and around 400. And for MC, you see a corresponding similar picture. As a summary, you can say that the samples can now be clearly distinguished and grouped. Means the special indices are clearly useful. You see, it is this is the deepest black sample with the corresponding undertone. So it's a positive undertone. It means it's on the bluish side. And also this one has a bluish undertone, and they give us the deepest black impression. So, and now in this table, you can relate the reflection value Y, for example, to the MY. You see here we add also a white, a mid-gray, and a deep gray, and you get no calculation for a white or a mid-gray or for a deep gray. The blackness indices are only for the deepest black colors. Okay, I don't want to show you only a comparison of these samples, but here you see from one sample every single measurement out of the 50. And this time it's not the calculation like MY, or this is the true Y number. And now please have a look to the scaling. Values only deviate from 0.0162 to 0.017. So as an average, after 50 measurements, we found the value of 0.0166. And the standard deviation is only around, you see, 0.0002. So this looks a little bit jumping, but it's a really stable result. Okay, now I want to compare the normal Spectro 2 guide, for example, instrument to the Pro model. Again, as a 6 samples, test 1 to test 6. And we measure both or all samples 50 times with both instruments. And the dark blue bars corresponds or shows the average of MY after 50 measurements with the Spectro 2 guide, and the light blue with the Spectro 2 guide Pro. And here you see the variations found in these 50 measurements. For the brighter samples, 1, 2, 3, so they are really deep black, but they are brighter, the brightest one in this sample set. We can only see a small difference between the normal Spectro 2 guide and the Spectro 2 guide Pro. So this is really the same. So this is due to the fact that the amount of reflected light is somewhat bigger than the signal to noise, and the signal to noise ratio is a bit better here. The darker samples here, the darker the samples, the larger is the difference between those two instruments. It starts here that the normal model shows a higher variation when looking to the 50 measurements. And here, the variation of the 50 measurements, it's again much higher in regards to the MY number. And here we get the highest variation. And the Pro models, you see, they are very, very stable. They show a higher number on a very stable level. So these Pro models, with the improvements, are really the best for checking those really deep blacks. Okay, where you can find this jetness mode in instruments, for example, you see here in the firmware, there are a lot of indices available, yellowness indices, whiteness indices, and we call it jetness indices. When you click on it, you can activate those indices and then you get them displayed. According to DENISO 18314, also special indices for gray are available. So, and you cannot really do anything wrong because the instrument guides you through. You see what happens when the gray is measured in jetness mode without activating the related indices, then you get a message. Yes, that you leave the range, the measurement range, and then you have to switch to a second set of indices. Okay, here also in the Smart Lab software, you can activate all these indices and then you see the complete data set if you like. You see, you have the LAB numbers, you get the X, Y, Z numbers, and you get the MY, the MC, and the DM number. And you can have, if you like, limits. You can define your own limits for the MY, the MC, and the DM. Okay, now the last part of the presentation is sample preparation. So Deep black can only be measured on high gloss and clean surfaces. The smallest changes to the sample surface lead to massive deviations in the values. Any con contaminants must be removed, and the panels must be absolutely free from scratches, fingerprints, and everything. And the problem is some of these dust, scratches, fingerprints are barely visible under normal lighting conditions. So I will show you some pictures. Here you see a dusty sample. Here you see a clean one. On a dusty, for example, we get an MY of 314, and on a clean one, it's the same sample, we get MY of 380, around 380. So the problem is this dust is not visible under, or it depends on the illumination and on the viewing angle to see this dust. That's why we add a flashlight into the delivery content. So why a flashlight? Here is the setup. To see the dust, the dirt on the sample, you really need to um, put the sample and the flashlight in the same plane, in the same level. So here on a desk and then beside the flashlight. And while illuminating under a very, very flat angle from the side, the dust is visible. So here, this is the same sample. And here you see the only dust particle you see here and here. Now illuminating from top and looking from top. Now we see these streaks. We no longer see the rest of the dust. So that's why I really highly recommend to check the sample surface of these deep blacks under those two conditions, or maybe also in between. Because these small, let's say three of them, have an impact on your values. That's why cleaning is so important. For cleaning, you can use distilled water, isopropanol, and lint-free cloth, for example. So you see here those you also use maybe for your glasses to clean them. And you need a lot of them. So cleaning, checking with the illumination viewing setup. Cleaning, checking, cleaning, checking. And sometimes you need 5 times of cleaning to get a perfect surface that can be measured on this deepest black. Okay, now to sum it up, deep blacks can be measured objectively, repeatable and reliable with these new instruments. And the measurement results obtained in the optimized jetness mode correlates with the visual evaluation of our test panels. And the Color to View Pro, the desktop instrument, shows really excellent repeatability on deepest blacks. And this has been tested by the company Orion. So we have developed these instruments together with Orion. Orion is a producer of these deep black pigments. So, and they are looking for an instrument that was able to measure those, because the other instruments, they cannot see differences in these test 1 to test 6 sample set. And available again is these instruments are as a handheld instrument called Spectro 2 Guide Pro, can measure all colors and the deepest blacks and gloss and fluorescence, and can check for fluorescence. So deep black, and a nice picture for that it also can measure color. and the spectral, the color to view. As a pro model, it measures color under 45 degree. It measures gloss under 60 and 20 degree. It checks fluorescence, and it can measure jetness. Okay, so before you leave, I will check your questions. And meanwhile, I show you some pictures of my colleagues and me and some contact data. So if you have questions later, feel free to contact us. So question, can you explain what the glance 60 column means? Okay, these are, I have no idea what slide it was, but gloss, it means gloss under 60 degree, measured gloss under 60 degree. Then the X, Y, Z used in MC are the same reference used in LEB. Yes, are the same values used to calculate LEB star. So signal to noise ratio of an instrument is also limited by stray light within the instrument. How do you mitigate unwanted scatter in the instrument? Okay, some I cannot answer. It's let's say company secret. Sorry. So because this is really tricky, and you have to find or we found a solution. Do these instruments take gloss into account when looking at blackness? So yes, that's why 45.0 is recommended. 45.0 excludes gloss the best way. So this is one way to take gloss into account, you know. And in addition, it measures the gloss level. Hope that answers the questions. And then the last one, are you going to share with us this presentation? Yes. We will send out the email with the PDF version of the presentation soon. Hopefully, we can manage it today. And in addition, we will put the recording of this web seminar on our website. Let me show you where you can find it. Quick, I will move our website here, switch it to English. So under support, you see seminars and web seminars. When you click on here, you can pick web seminars. And here you have all the web seminars listed. And when you click on here, later you can find, when you scroll down, the link to the recording. This was under support. When I click on products, for example, color, then I can click on the color to view. You have seen it during the presentation, or I can click on Spectro to guide, whatever. Let's pick Spectro to guide. Oh no, that okay. We have also videos. Let's click on the color to view. And then anyway, you can click here or here, click on Color to View Pro, for example. With a lot of products, you find when scrolling down an option called knowledge. And under knowledge, you have downloadable PDFs. Here, basic building blocks of color, color measurement of fluorescence, or color measurement of black. Clicking on read more opens the document. You can download it, and you may see some pictures you have seen before and a lot of background explanation related to the topic. So feel free to download these PDFs. Okay, so let's check if there are more questions. Okay, maybe the last question for today. I have a Spectro Guide 450 gloss. What is the difference between the equipment? So the Spectro 2 Guide the Spectro Guide was, let's say, we started with the Spectro Guide 15 years ago, or yeah, around that. So the Spectro Guide was an instrument, the same setup, 450. And you can measure color, fine, but the Spectro Guide is not able to differentiate those deepest black. It's made for normal color measurement. In the world of normal color measurement, it works fine. With the new generation, so we improved a lot. So we improved inter-instrument agreement. We add that you can check the fluorescent components if you have fluorescent components in your coatings. And the new models, as always, new generations have always a better repeatability and inter-instrument and a better inter-instrument agreement. It's just the improvement you have from one generation to the next. Okay. And if you want to measure really the deepest black, you need the new generation model and the pro version of the new generation of the instruments. Okay, so before running out of time, let me show you a last picture of our company. So BYK-Gardner is a German company. It's located close to Munich. The town is called Geretsried. Here you see some of our buildings, and these are nice pictures of the area around Geretsried in summer. Okay, what's left is thank you for your participation, and I hope to see you next time. Next time means next year. So yeah, happy holidays, Merry Christmas, and Happy New Year. And I wish you all the best. Und ja, fröhliche Weihnachten und ein frohes neues Jahr auf Deutsch. Hope to see you next time, and I wish you a remaining successful week. So bye bye for now.